We talked about the local distance ladder, H0 from the CMB. We presented the recipe for how we're going to extract H0 from the CMB. Then we used the Newtonian approximation. We talked about fluctuations in the number density of photons. We saw how to introduce perturbations into the equations that we had, continuity equation, Euler equation, Poisson equation. Combine all of them. We added the expansion. We got the oscillations. Okay. We saw the damping effect. And then we saw how to move from these 3D spatial density fluctuations to the angular power spectrum of the CMB. So today we're going to pick up where we left off this year. And we're going to go back to the perturbation in the expanding universe and talk about subhorizon versus superhorizon. Perturbation evolution. And then we'll talk about baryons and BAO. And then we'll put everything together and at some point, I'll move to slides to sort of summarize what we did and talk about the prognosis of all of this. Okay, so let's start from where we left off. So back to density perturbations in expanding universe. Okay, now we want to discuss matter perturbations. Okay, so no longer talking about just photons. So we need the physical velocity of a particle. That's u, which is r dot, which is given by hr plus v, where v is ax dot. Okay? And I remind you the relation between physical quantity and the co-moving quantity. Okay? All right. So from this, we get that u as a function of space and time is given by h a. Sorry, I need to have the eraser much closer to me. Plus v x of t. Okay? So now the first exercise that you have to do is to show that the equation for the perturbations is then given by this. Okay, and I'm going to sketch how this is done. So I'm going to give you several sort of exercises like these over the course of the lecture, and I'll try to sketch how the solution is done, but you'll have to fill in the details. Okay? So the continuity equation was d rho dt plus, in an expanding universe, okay. Yes, I should mention this. Thank you. Now we are no longer talking about perturbations in the number density like we did for photons. Now this is for energy density. Okay, so the relation is this. Okay, the number density is related to the energy density by this.
So that's for baryons?
That is the dominant term, yes. Yeah. Okay, so what we do is we take the our equation, okay, and we can show that this becomes okay. Where to do this, we use the fact that okay, and this, and we take the perturbations, we get this equal to this. Okay, where I just plugged in, now I plugged in the perturbations. Okay, remember how we define them? Okay, and this is given by.
So everything is just the Barians, or do you have a couple Barian photons?
Now we're talking about matter, just the matter.
Alone.
Okay,
No
alone.
photons.
Yeah, no photons for now, unless I mention them. Okay. Now, since rho goes as 1 over a cubed, we get that delta equals, you can check this. And now we take the time derivative and we get okay? And if we plug this into the right-hand side of the Euler equation that we wrote, then we get okay? And if you take the gradient of this, sorry, not the right-hand side, it was the left-hand side of the equation. And now you take the gradient and you get that okay, and this you equate with the right-hand side of the equation. So you see where this showed up, okay? And that's the Hubble friction. So this is a new term that we didn't have before. It is called the Hubble friction. Okay?
Sure, considering only Barians with no photons, then the pressure is 0. So what is the definition of a source field?
If I what? Sorry?
You're considering only Barians, so no pressure. So what is CS?
So let's continue and we'll see, okay? So what are the relevant scales? The relevant scales are the gene scale, which is given by CSC and the particle horizon. All right? Okay. Now, let's ask a question. So it's clear that this particle horizon is just how much a particle can travel. This is the physical quantity. Okay? All right. So can we have perturbations outside the horizon? Does it break causality? You would think so, but still the answer is yes, we can. And this is because of inflation. Okay? Inflation's...
That's where the perturbations came from in the first place, though.
Sorry?
You said that's where the perturbations came from in the
Yeah, that's right. So that's why they can be also super horizon. That's the point. Okay? So the inflation stretches the quantum fluctuations well beyond the horizon. So let's sketch how that happens. Okay? This would be the co-moving scale as a function of time. Okay? This would be an example for a scale. And now what happens is that this is how the co-moving Hubble horizon looks like. Okay? Which is what we see here. So this is the period of inflation. Inflation, if you want to think about it physically, inflation stretches out the horizon. So any perturbation at some point, while it's subhorizon before inflation, at some point during inflation, it becomes superhorizon. Okay? So this is the point of horizon exit. Okay? Here, before this, we have quantum fluctuations. They're stretched out well beyond the particle horizon. But then, after inflation ends, the universe starts expanding regularly. And more as the universe expands, more and more fluctuations come into the particle horizon. There is more time for them to get into causal contact. So at some point, there's a horizon entry for the scale. Okay, so they enter back. Sometime after this is the moment of decoupling or recombination, or the last scattering surface, where we have the temperature fluctuations that we saw. And then today, what we measure is these C sub L's. And now the question that we're going to ask ourselves is, for all of these modes, this moment of horizon entry, okay, does it happen? We know that CMB happens during matter domination. Okay? But the modes can enter either already at matter domination. If CMB is at redshift 1100, matter domination, so matter domination and radiation domination, this is equality that we defined last year. This was at 3400. Okay? And now the question is whether the modes enter before or after this. Okay? Smaller scales, they exit last and enter first. Larger scales, they exit first and enter last, because it takes more time for the universe to expand so that large scales can be in causal contact. But smaller scales, they already, at the beginning, very quickly become in causal contact. Okay? Questions so far?
Why does the horizon get smaller during inflation?
So you can think of it in the opposite way, where inflation stretches out the fluctuations beyond the horizon. Okay? If the horizon is this, what happens during inflation is that this gets very small. Okay? You can show that. We might do that tomorrow. But I'm going to use that for now as a given.
Ask about you said that believe that the perturbations are not causal. They are superhorizon.
If there wasn't this sort of effect, there would be no time for these fluctuations to form. Because of inflation, you can take these quantum fluctuations here and then form them here where they're subhorizon, and take them superhorizon and come back.
So
Okay, but this allows them to form to begin with.
in the universe that this didn't happen, what do you expect?
Universe what?
In the universe that this didn't happen.
I don't understand what you're saying.
In the
Universe what?
universe without inflation. Okay?
In the universe without inflation, you wouldn't
What do
have
we
this.
expect? That we do
In a
not
universe
expect
without inflation, you would not have these superhorizon and subhorizon modes.
But this-
You will never create the superhorizon fluctuations unless there's some mechanism
what
to
will
do
it
that.
be? So would you expect to have uniform thing, or do you expect that the perturbation will be non-Gaussian? What do you mean that?
How would you form non-Gaussian perturbations if there was not, if
Something will happen. Do you expect that things will be just the same temperature, will be uniform?
I don't expect anything because I don't expect any kind of fluctuations to happen in the first place.
So that means you'd expect. So that means that there would just be a uniform distribution.
Depends on the model that you have, okay? But that cannot explain the universe that we observe, okay?
Yes, but you said that this will.
The question is whether there are superhorizon modes.
Yes,
That's
you
the
said that
question.
This will violate causality. What will
If you
violate-
want, the violation of causality would be the creation of perturbations while they're superhorizon. There's no way for that to happen. If you want to generate the perturbations while they're superhorizon, they're not in causal contact. If you want that to happen, I don't know, you have to come up with some mechanism to do that, to generate a perturbation that is superhorizon. What inflation does is take subhorizon perturbations, which can be created, and stretches them out so that they're superhorizon. Okay? And then they come back in.
Okay, so you need inflation in order to correlate to
That's right.
perturbation,
That's right.
not in order to produce perturbation.
No, the perturbations are quantum fluctuations
Yeah, but
that were there.
But there is-
Inflation just stretches them out. That's what it
there is
does.
a big difference between no perturbation and no correlation between perturbations. That's two different things.
That's right.
So
Inflation generates both.
yeah, but it's the thing that you expect from inflation that perturbations will be correlated.
It generates.
But you do not expect that perturbation will not.
But let's leave this for discussion afterwards, okay? Because we're not going to
Sorry, I think,
be able to say anything if we
I
continue.
think
with
it's
it. Yes.
1 over h together, right?
Yeah, of course. Thank you. Of course. Thank you. All right. So the sound speed is much smaller than the speed of light, which means that it is always the case for these matter perturbations that we are the gene scale is well inside the horizon, so both sub-horizon and super-horizon modes suffer the gene's instability. Okay, now if k over a is smaller, much smaller than the gene scale, then the equation looks like this. exercise, check that you get and again, I'll sketch how you do this. You plug in 8 squared equals 8 pi g over 3c squared rho. And you use the scale factor in matter domination, which goes as t to the power 3/2. 2/3? Yes, that's right. And then h is 2 over 3t. And then you substitute delta as a power law in time into this equation. And what you get is that the perturbation has a growing mode that goes as A and a decaying mode that we don't care about. Okay? So we have one result. Let's note here that this growing mode is now growing as A. Well, when we solved things last year, we didn't have the Hubble friction term. And we saw that when there was a growing and decaying mode, when modes were suffering the G instability, we saw that the growth was exponential. Okay? So we see that due to the Hubble friction, which now shows up, perturbations only grow as a power law. Okay, now let's talk about growth of perturbations in a radiation-dominated universe. Now I'm looking at the matter. And I can write that in general, the matter receives contributions from all the components of the energy density. Okay, so this receives contributions in the Poisson equation to the gravitational potential from all components. Okay? But in radiation domination, we know that what dominates the density is the energy density in radiation by definition. And so we can ignore delta m rho m. This is much smaller than h delta m k.
Sorry, before you read that,
Yeah.
What do you mean by both subhorizon and superhorizon suffer gene instability?
The gene instability is much smaller than the horizon, so it is always we always need to take this into account. You'll see the opposite case happening with radiation and matter right now. Okay.
Sorry, but what physically does it imply? Does it imply that the perturbation collapse or dissolve or grow?
They grow.
So So it implies even super horizon, it can, right? On super horizon scale, it can go.
Super horizon, of course, the fluctuations do grow outside the horizon. The fluctuations do grow outside the horizon. That is the whole point of what we're deriving. Curvature perturbation doesn't, but these density perturbations, they do grow outside the horizon.
Is it gauge dependent, this statement?
No. Okay, so outside the horizon, we are left with just this component. Okay. And now the exercise would be to repeat same steps that we had here and find for radiation domination where A goes as t to the 1/2 and h goes as 1 over 2t, that the fluctuations have again a growing and decaying mode, and the growing mode goes as a squared. Okay, it's just a matter of plugging into this equation this different time dependence, again assuming that delta is a power law in time, and you get a growing mode that grows faster. But what happens on subhorizon? Subhorizon, we know that perturbations in the radiation do not grow, right? They oscillate. They don't grow. That's what we saw last year. So that means that we get a different equation for the subhorizon modes, which only has these terms. Okay? And the solution for this is that the perturbation goes as either log of A or it is a constant. Those are the two solutions. So again, the growing mode that we care about grows as log of A. So this is not much of an impressive growth. Okay? So what's the conclusion? The conclusion from playing this game and following the evolution of modes inside and outside the horizon at radiation domination, depending on whether they enter the horizon at radiation domination or at matter domination, is that during the radiation domination era, matter perturbations inside the horizon only grow logarithmically, which means there's significant growth in subhorizon modes starts only at redshift of 3400 or so. Okay? Only at matter radiation equality.
Sorry, on the left-hand side, the del m belonging to a squared or a minus 2, that's the superhorizon?
Sorry?
What is the first?
So let me sum up. Let me summarize.
No, sorry, but what was that on the first piece of board? That was superhorizon?
Yeah, let me summarize. Okay, so we have inside and we have outside, and we have radiation domination and matter domination. Okay, and what we got is for inside the horizon, at radiation domination, perturbations grow logarithmically. Outside the horizon, at radiation domination, they grow as a squared. Inside the horizon, at matter domination, they grow as a, but it doesn't matter. They grow in the same way inside and outside in matter domination. Okay? All right. So, scales entering during RD experience a deficit of growth. That means that if we start with some initial power spectrum of fluctuations, let's take it as a power law, and from inflation, we know that the power law is almost 1, but that's not terribly important. We know that the power spectrum in the matter perturbations will now look like this. It will have a transition. Okay? At matter radiation equality, instead of growing, so the exercise will be to show this. Instead of growing, it will be dropping like k to the minus 3. Okay? The reason we have this a squared growth results in a k to the 4th relative power behavior of the matter power spectrum before and after, or before and after matter radiation equality. Just to check that you're with me, things here are in radiation equality, are in radiation domination. They enter at radiation domination or at matter domination. These perturbations, the smaller ones. Smaller ones enter at radiation domination, or do they enter at matter domination? Radiation domination, right? Because they exited first, they entered first. Remember this plot that we had? They exited first, they entered first, and radiation domination happens before matter domination. So these modes, the smaller modes, enter at radiation domination. Because of this effect, because of the deficit of growth of these perturbations relative to the perturbations that come in at matter domination, we see that the power spectrum of matter falls for the smaller scales. Okay? So that's a summary of what we have. Okay. What is the implication for the CMB? The implication for the CMB is that we see a similar behavior. Meaning a difference between modes smaller and larger than K equality. What happens is a little bit more complicated, and I'm not going to be able to show that with the approximated Newtonian derivation that we did before. But what happens is that modes that enter the horizon at radiation domination are smaller modes. Okay? And for them, for these modes, the pressure dominates. Remember we saw that for small scales, the pressure dominates over gravity. And then that prevents further compression. Because the modes oscillate. Perturbations don't grow, they oscillate. That's what we saw as we saw. But in radiation domination, it is the radiation that dominates the gravitational potential. Therefore, the potential decays as we go to smaller and smaller scales. If the potential decays as we go to smaller and smaller scales, this boosts the oscillations. Okay? So what we end up getting is that if I plot LL plus 1 CL over 2 pi, this is the power spectrum that we measure. This would be the power spectrum if there weren't any damping. But there is damping that we saw last time. So this is what we see. This is called the potential envelope. Okay, so this is the boost that we get. And this is sensitive to how much matter versus how much radiation there is. Okay. Questions so far before I move to the baryons and how they affect the power spectrum.
Where did the horizon come in the equation of motion?
Where did the horizon come in?
You had two different solutions depending if you were super horizon or sub horizon.
That's right.
Where was that in
Whether we took K over A or the gene scale.
and what was K equality? Did you define that?
That is what is relevant for the gene's instability. Yeah. Sorry.
K equality. K on the second line up there.
Yeah. This.
What's that?
K equality is the scale at which matter domination. We switch from matter domination to radiation domination to matter domination.
It's a redshift. What is K?
It equals AH, where H is at the moment where equality happens.
In summary, you said that in matter domination, the perturbation grow like log A outside the horizon, and for matter domination, they grow like A. But outside the horizon, the first one grows like A, and the second like A squared.
So I think you got it a little backwards. So what I said is that inside and outside, here in both cases it's A, this is A squared, and this is log A.
Okay, so outside the horizon, it actually grows faster for radiation domination.
Outside the horizon, it goes faster for radiation domination. That's right. This is for the matter perturbations. Yes, that's right. It's also for the radiation domination. This also happens for the radiation domination. Yes.
Yeah, I understand that you just compare the Hubble friction with the collapse scale, right? So
Mhm.
in this sense, because the pressure is so small, even the Hubble friction cannot stop the collapse. In that sense, cannot stop the growth. But it's super horizon.
But it does slow it down.
Right.
Yeah.
But still, I mean, does that have anything from the causal point of view? How do you make sense of growth on the super horizon scale?
So this
There should not be any correlation.
So this is not the way. This is not the way you should derive things. Okay, this is just in the Newtonian approximation. So this is just a sort of sketch for how things happen in the real world. In the real world, you should not be using the formalism that I used here. You should be using the metric for the density fluctuations in GR, and when you do that, your intuition would work better.
So about this comparison, if it grows faster outside the horizon, if a mode that enters very late after radiation domination doesn't have a lot of time to grow before it enters the horizon?
Again, a mode that enters very late in radiation.
Outside the horizon, it's the radiation dominated modes grow faster than matter domination.
No. This is what happens. This is all for matter perturbations, right?
Yeah.
Depending on whether they're inside or outside during radiation domination or during matter domination. They can't be all over the place. Okay, the same mode cannot be in all four places here.
Oh, but on a certain point, the mode enters the horizon. So
That's right. And the question is whether it enters at radiation domination or at matter domination. Yes.
Just a simple question to make sure I'm understanding this. Can you just briefly say the difference between the sub and super horizon?
The sub and super horizon. So again, the question is whether. So we had that before, right? So I'm not sure what. The question is how these terms, okay, all behave with respect to one another. Okay? So we have this scale, okay, which is the horizon. And then we have the gene scale, which we saw goes like okay? And so one question is, how do you compare these two? And if you can neglect one versus the other. And the other question is, how do these behave versus the Hubble friction? Okay? And that is determined by the relation between the modes and the horizon distance. Okay? So it's just a matter of which terms are dominating. Okay. So let's move on to the baryons.
Just one last question about
Yeah.
this potential envelope that you said, which is sensitive to how much matter versus radiation.
Mhm.
We're never actually measuring that potential envelope, right?
So you can explain the damping. You know how to calculate the damping effect. So you can sort of de-damp your measured power spectrum. If you de-damp it, then you are measuring, in fact, the potential envelope, which is sensitive to this ratio.
And there'll be no ambiguity in that damping. That damping is
just particle physics?
yeah.
So the damping, okay, so that's what I'm going to emphasize now. The damping has to do with rho baryon, and not with rho matter. Okay, because the damping had to do. Remember that we saw that in the last time. The damping had to do with the free electron fraction. Okay, so this has to do with rho baryon, and that's a separate thing. Okay, so these are not completely degenerate.
You have degeneracy with initial condition.
You have what?
It will be degenerate with initial condition.
Generate with the initial conditions. What do you mean by that?
So when we talked about oscillation last time, we normalized to the initial condition,
Hmm.
but you don't know that.
But we normalize everything to the same,
Yeah,
the
but
same,
when you
because
measure, you cannot. The measurement itself is not true. If you modify, if you undamp the damping effect,
mhm.
then it will be degenerate with your assumption of the initial condition.
But we
Yeah.
assume
The envelope and the initial condition.
the perturbations are the same perturbations in all the components, right? This fluctuation, the initial fluctuations are from inflation are adiabatic. I was going to say that in 2 minutes, but that means that the initial fluctuations are the same in all of these. Okay, so that's
What is equality in this one?
good question. Equality in this plot is around here.
And then how does I convert K into L?
That's something like 233, if I remember correctly. Yeah, that's after you convert from K to L, exactly. Yeah, that happens around here. This is why it's only here that the potential envelope actually starts growing. And it asymptotes because at some point you just decay completely away. For very, very small scales, there's no contribution to the potential, so there's no more of this effect that you're boosting the oscillation because the potential decays. It has already decayed so much that it's unimportant. Okay, so let's talk about baryons. So as I just said a second ago, the initial perturbations are adiabatic. This is from inflation. That means that all delta I are equal, where I stands for matter, radiation, baryons, etc. So now consider an overdensity.
So you're just reminding in your notation that so matter is what's the difference between matter and baryons? Matter
This is cold dark
baryons
matter. I
plus-
mean cold dark matter when I say matter. And this is baryons and this is radiation.
So matter is baryons plus cold dark matter or just the cold dark matter?
So it doesn't, yeah. The part that is relevant here is the cold dark matter. Only the cold dark matter, not the baryons.
Okay, but when we were doing the matter,
But
when
it's-
we were doing these fluctuations before, that was for the baryon component or the cold dark matter or the sun.
No, so omega m, this is the total. Sorry. Omega m is the cold dark matter, and we have omega baryon, and then we have omega lambda. Okay? So we separate between them.
Okay, so cold
So
dark
this is
matter
cold dark
and
matter,
baryons.
this is baryons, and this is lambda. Sorry. Okay? It's true that in a lot of places you group the matter and the baryons together and talk about the total matter. But what I'm talking about is the cold dark matter.
You're saying that the potential envelope it doesn't care about the baryons, or it does, but you could just.
So it's a little more
work with
complicated.
it?
It's a little more complicated than that because baryons, I'm sort of separating between, until what I'm going to say now, I've separated between the radiation and the baryons. But the radiation and the baryons, photons and baryons are tightly coupled through constant scattering, and so they're really I can't do what I did also in the last lecture, where I just treated the photons separately, and I assumed the speed of sound was 1/3 c squared. This I can't really do, okay? Because in practice, this is a tightly coupled fluid, and I should treat them both together, and they have a modified speed of sound. But I'm going to say that right now, okay? But this behavior is not, so this is really, yeah, okay. That's it enough. Anything I say more will just be confusing. Okay. So let's assume we have an initial overdensity. Okay, so these are all the components are in some overdensity around some center. Okay, some center of the overdensity. So this is the profile of this overdensity. But imagine that you have an overdensity of baryons and matter and radiation. What would happen? Because the radiation and the photon baryon fluid is compressed, the radiation pressure will tend to push the baryon photon fluid away. Okay, so the dark matter will stay, but the baryon photon fluid will move away. So this radiation pressure pushes away the baryon photon fluid. Okay? But then, at some point, the baryons and the photons decouple. So the photons just keep moving away, but the baryons stay frozen in place because their speed of sound is very small. And the perturbations also grow with time. So dark matter perturbations then grow. And then you have another smaller perturbation. So this would be dominated by the dark matter. And here you would have the baryons. Okay? Frozen at some distance, which corresponds to the, so this is exactly the sound horizon.
Why
Okay?
don't the baryons grow as much as the dark matter is?
Why don't they grow as much? There are less of them. And the potential of the dark matter is much stronger. So the dark matter accretes much more matter here. The baryons, they're just pushing. They're not accreting anymore to them. They're just the same size that they were in their contribution here, and here, and here. They remain of the same size. But here, there's this grows. Okay? So this is what happens to an overdensity.
But this is a gravitational collapse, the growth of the dark matter, right?
Yeah. It's the same growth that we described with our equations before in the last part of the talk. Okay. So what are the implications of this? If we look at the galaxy correlation function, for example, we can actually see this effect. So let me explain what the galaxy correlation function is. The galaxy correlation function is the excess, two-point correlation function, is the excess probability, that's what I'm plotting here, the excess probability relative to a Poisson distribution to find two galaxies separated by a co-moving distance r. Okay? So this picture, what it creates, it means that everywhere where there wasn't an overdensity, there is now a large overdensity that evolved, and at a distance matching the sound horizon from it, there's another overdensity, much smaller. But there's nothing in between. Okay? So this means that this would be the two-point correlation function of galaxies. Okay, where this is the co-moving sound horizon, which is of order 100 megaparsec. Okay? Let me write this down. The BAO scale corresponds to the co-moving sound horizon at recombination. Let me put an asterisk here because I'm going to get back to this in a second, which is imprinted onto the baryon density field. Okay, and if we look at the total matter power spectrum, so the total matter power spectrum, before I was just looking at the cold dark matter, the total matter power spectrum looks something like this. Okay? Where this is K equality. So remember we had this behavior before for the power spectrum? Now we have these wiggles here. Okay? Why do we get wiggles? This is the BAO scale. This is in configuration space. If you take a power spectrum, a Fourier transform of this, you get wiggles. A Fourier transform of a delta function gives you a sinusoidal behavior. Okay, so in the total matter power spectrum, you get these wiggles imprinted on it. Okay.
So does the peak in K-space correspond to any features in the silicon space? That small peak corresponds to the wiggles in the K-space, and if you do the Fourier transform the other way, does the big peak in the K-space correspond to any features in the two-point correlation function? I mean, I've never seen anyone talking about this, but I just wondered.
Yes. What's the question?
For
Does
small
K
peak in
equality have an imprint back on real space?
Right,
Your peak,
so-
your peak in K spectrum.
right,
Ah.
big peak.
Right, that's your question?
Yes. Thank you.
Good question. What would? So you're saying you would get what? You're expecting to see some wiggles, some oscillations in real space corresponding to this
Right.
peak.
Right.
Uh,
Unless it's Gaussian, then it corresponds to another peak.
Yeah, that's a good question. I don't know the answer. I need to think about that. Okay. So what are the effects?
100 megaparsecs is the time, not a recombination. Is distance not a recombination.
Sorry?
100 megaparsecs. Distance today?
It's a co-moving distance, so it's the same.
Right. But it's
Now it's 100.
no, it doesn't say a recombination.
So the effect on the CMB, it's the same, right? I didn't understand. Okay, okay, we're fine. All right. So what are the effects on the CMB? There are several ways by which the baryons affect the CMB power spectrum. First, they provide loading onto the photon oscillations. Okay, because they have excess mass that also helps to and affects the compression of the peaks. Okay, it increases the compression and lowers the. So this, let me just write it down. It affects the even to odd peak ratio. Okay? It enhances odd peaks over even peaks. It also alters the 0 point of acoustic oscillations. And this is because the speed of sound in the baryon photon plasma is affected by the ratio between rho b and rho gamma. So instead of the pure relativistic case, we now have a different relation, which I can't derive with the tools that I've had here before. Now the speed of sound is modified, where this r has to do with the fact that the baryon photon fluid is a tightly coupled fluid due to Compton scattering. Okay? So baryon photon fluid is tightly coupled due to Compton scattering. There's momentum exchange between the baryons and photons. And the relation is through, if you look at the Poisson equation, the continuity equation, this density, this factor is what I had here. And this is roughly given by, okay? Because this is negligible, this is 1/3 this, and so this is roughly this. Okay. So we have this effect, and CS, or CS squared, it depends on this now.
What's the difference between the even and the odd peak?
The compression, or the opposite of compression.
What do you mean that it alters the 0 point of the
So because the sound speed is different, where the first peak arises, which is at k star, k equals k star, that's what we saw last time, it moves. It will be different because this would move also. Okay? Compared to the calculation that I showed you last week, which was an approximation. Okay. So now we can move to extracting the parameters from the CMB. So what are the quantities that we saw and that are important? First, there's the co-moving sound horizon at, I remind you, we had this last time, the co-moving sound horizon at the last scattering surface, which is okay, which is given by this. Remember, we saw this last time. So we need to be able to calculate this. Remember the prescription that we had? I don't know if you remember, but the prescription that we had for extracting H0 was first to measure this, then to measure this, then use the fact that the angular diameter distance is equal to the ratio between these two. And then from the angular diameter distance, we can infer h of z, and from that we can infer h0. Okay? So that's why we're interested in this. So what is RS depending on? RS is dependent on, it depends on CS which is a function of rho b over rho gamma. Okay, this we just saw here. And it also depends on h of z, which we know from the Friedman equation is given by this. Okay, so it depends on rho m. So we need to know rho m, and we need to know rho b. But we just said how we could measure rho b and rho m. Rho b we can get from I forgot to say that there's another way, another effect on the CMB, which is the damping. Okay. So this you can get from the damping scale, for example, or you can get it from the peak ratios, from the even to odd peak ratios because of the baryon loading effect. That's how you can get rho b. Rho gamma, remember, we get from the temperature, T gamma. And rho m you can get from the potential envelope that we just described. Okay, so this you can get from damping or peak ratios. Okay. Let me get back to the asterisks that I had before. And note that we need to distinguish between RS drag and RS star. Okay, RS star is the co-moving sound horizon at the last scattering surface. RS drag, let me define what that is. This is relevant. This is the co-moving sound horizon where radiation drag stops, okay, or becomes no longer dominant. This is not the same as this. Okay, and why is that? Because of the baryon to photon ratio, which is huge, or the photon to baryon ratio is huge, photons stop caring about baryons before the baryons stop caring about the photons. Okay, is that clear? So what's actually relevant for the baryons, for the baryon acoustic oscillation, is this RS drag and not RS star. But the difference is not that big. So RS drag is something like 0.98 of RS star. Okay, so it happens, this moment happens a little bit later. Okay, so we have RS star as a function of rho m and rho b. Now, theta s star we get from the peak spacing. This we saw last time. The delta L peak goes as dA star. Yeah, we saw this last time. Okay. Let me not write more. And so if we get from the peak spacing in the power spectrum, we get theta s, and from rho m and rho b, we get R of s, then we get dA star, and from dA star we get h of z, and from h of z we get h naught. So at the end of the day, if you take Planck data, what Planck data shows us is that this is the result. Okay? So this is very different than what we got from the local distance ladder. Remember, from the local distance ladder, we got something like this. So this is the Hubble tension. But we have to talk about the role of BAO to fully understand what the tension is. Questions before I move on?
Yeah. So in H of Z, it's not fitting to the function H of Z. It's putting in rho m, rho omega, rho lambda into H of Z, and passing
Yeah.
those and then inferring H.
No, so here you set, here what you do is you set rho lambda so that, this we talked about last time, so that dA equals Rs star over theta S star. So you measure this, you measure this. Now you know, now you have to get the dA equals this. Okay, but dA star is the integral from today to, it's the integral of this, okay, from today to the last scattering surface. So here, this H of Z is not just dependent on rho gamma and rho m. Here I didn't have rho lambda, right, because it's 0. Completely negligible at recombination. And for Rs star I just erased, but this was, remember, from Z star to infinity, the same integral. But now I'm taking this integral from 0 to Z star. So this H of Z, it does care about all the components.
Yes, CS is
No, sorry, no CS. What did I, sorry. I'm sorry. This is how we defined the angular diameter distance yesterday, right? So, but this H of Z does care about this. But you know what it has to be. So now you can set rho gamma such that this is equal. That's that we said on Monday. And if this is the case, then now you know H of Z, now you know dA, and you know H of Z. And if you know H of Z for all Z, you also know H naught. So that's how this is done. Okay? All right. So now the role of BAO. So we can also try to measure by looking at the statistics of galaxies. Okay, so these would be galaxies and galaxies. In some, imagine these are two redshift slices. Okay, some redshift slice. This is a redshift slice. And I'm trying to measure the BAO scale by looking at the correlation function or the power spectrum of these galaxies in these two redshift slices. I know that there's a scale there that is imprinted onto this, right? And the co-moving scale is the same scale that is imprinted in both, on the statistics of both. But what I'm measuring is not this distance. I can't measure distance. What I'm measuring what we measure is not distances. We measure angles and redshifts. Okay? So now the question is, how do angles and redshifts towards some physical size change? Okay? So the co-moving size of an object or feature at redshift z in line of sight and transverse directions, so r parallel and r perpendicular, behaves like this. Okay? And so from this we see that if we're sensitive to changes in z and theta, what we are actually measuring has degeneracies. In this case, what we're actually measuring, these two quantities that we're trying to measure, these fixed co-moving sizes, are the BAO scale RS drag. Okay? So in our case, this goes as RS drag over dA, and this goes as RS drag times h of z. So we can't disentangle between RS drag and h of z. We're only sensitive to the multiplication of these two. And the same goes for this. Okay? So that means we have to calibrate the BAO measurement. So what are our options? We can take BAO.
What are we measuring in BAO?
You're measuring the scale, this RS drag, which is you can think of it as in the 2-point correlation function, you can think about it, you can think of this, for example. What you actually do is you measure the power spectrum, usually, and take it from the power spectrum. You see the wiggles. You fit for the wiggles, and that gives you the scale. But you can also do this in real space.
But we do it along the line of sight and in the direction? There are two measures?
Yes, I mean, what you actually do is you take the power spectrum of the galaxies here.
Three-dimensional power spectrum?
The three-dimensional power spectrum. Okay, what you actually measure is the three-dimensional power spectrum. And the three-dimensional power spectrum receives a correction that goes like this, and a correction that goes like this. Like this.
So you need to
Okay.
measure angle, redshift, and flux.
Yes. That's right. But what's sensitive to what we want to measure is the angles and redshifts. Okay, so one option now to do the calibration is to take BAO, so that's a measurement of RS drag times h of z, okay, and combine it with the shoes measurement of h naught, okay. So you set RS drag so that h naught matches. So you take the h naught of, so in essence, you take the h naught from shoes and you infer RS drag. Okay, so that's one way to do this. Another way to do this is to take BAO with a CMB. So here you set RS drag from CMB, and you get h naught. Okay, this is sometimes called the inverse distance ladder. That's another option. What you could also do is you take BAO and you combine it with BBN. Okay? So you use the deuterium abundance to get rho b. So let me say something about this here. So I'm opening a parenthesis here. I mentioned BBN in my first lecture, but let me go back to that. So the deuterium formation is via a process of n plus p going to d plus gamma. Okay. Now you would think that the deuterium, naively, okay, you would think that the deuterium synthesis would happen once the temperature matches the binding energy of deuterium, which is around 2.22 MeV. Okay, so this is the binding energy. But because the photon to baryon ratio is huge, even the tail of the exponential tail of the black body distribution is enough to dissociate the deuterium. Okay? So what you actually get is that synthesis actually begins at kT, which goes like the binding energy over minus log eta, where eta is the baryon to photon ratio. Which we know is something like 5 times 10 to the minus 10. Okay? So the deuterium abundance, if we can measure deuterium, the deuterium abundance is very sensitive to this number. If it's sensitive to the baryon to photon ratio, we can get rho b from this. Okay? So you use deuterium abundance to get rho b. But then, if you add...
But the deuterium forms other elements after, right?
Yes, but these are processes we can track analytically and understand. We can compute what we expect those rates to be, and then we can go backwards and find this. BBN is very well understood.
Sorry, when you say that BBN is ineffective, that ineffective is just radiation, doesn't have to be photons, right? So how does it fit into this argument? If we throw in extra radiation, actually it doesn't really contribute to the dissociation of deuterium, but why does that constrain the...
So throwing in extra radiation changes things.
Right, but how? Through the temperature?
Yes, exactly. It does change the temperature history. I've ignored neutrinos completely, okay? But neutrino in my talks, because they provide a correction to what happens for photons. But it's true that if you have neutrinos, the thermal history is a little bit different, right? Because you have to take into account the contribution. And if you have a larger a larger number of relativistic degrees of freedom, effective relativistic degrees of freedom, then that would change also. So that's true. If you change an effective, things like this would change. But assuming the standard LambdaCDM, and you know everything, you know how to compute everything, then you can get rho b from deuterium. Okay, that's the point. Now, if you add weak lensing, so for example, you use omega matter from some galaxy survey, so I haven't talked about weak lensing. But weak gravitational lensing is something that affects the power spectrum of the CMB and also of galaxies. But if I want to circumvent the CMB and not use the CMB, I can measure weak lensing and the effect that it has on the power spectrum of fluctuations, and measure omega matter from this. And then I have rho B and I have rho M. Okay, if I have rho B and I have rho M, that's enough to get H naught without using CMB anisotropies. I still need the temperature, the CMB temperature, because I need rho gamma. And that I get from the CMB temperature. But I can get H naught from this method without using CMB anisotropies at all. Okay, that is the point. Sorry?
Rho lambda.
Rho lambda.
You get that from CMB?
No, the rho lambda I didn't get from the CMB. I got from the measurement of RS and theta S, the peak spacing. So
Theta S is from CMB.
that's right. So what you actually do, is you get but if you have rho B and you have rho M, then you know because this is
omega equals 1.
yeah. You assume flatness, so you get omega. Okay, so what you get from this is 67.4 plus minus 1.1. Okay, so this
That's in between the two other ones?
sorry.
That's in between the two other numbers?
No, it's exactly the same central value as the one from the CMB, just slightly higher error. So this is still using early universe physics because I'm using what happens at BBN, okay? But I'm not using CMB anisotropies, and I'm also using the CMB temperature that we measured from PHI-RAS, from COBE, but we're not measuring anisotropies, and we still get this. So even if something is wrong with Planck, there's still a problem between early and late universe measurements, unless there's something wrong about these measurements as well, which could also be the case.
And checking omega M from the galaxy survey there are no other dependencies that are hidden in that expression?
Well, there always are, but not ones which you can solve without ruining other things. But these are completely independent of the CMB anisotropies. That's the point. I mean, of course, there are systematics related to this and systematics related to that. Okay, so if we put everything together, what we get is that the tension should actually be viewed in an H naught RS drag, and sometimes you'll see RS star if you look at plots of this, because the difference between them is not very large, but just if you look at the literature, you should appreciate that there's a difference here. So you have this is what Shoes tells you. Okay, you need to be around 74.
What is the shoe number?
Sorry?
What is shoe again?
Shoes is the local distance ladder. The measurements using the Cepheids and the supernova, the type 1a supernova that I talked about at the first part of the last lecture. What BAO does is it forces you to live here. Okay?
BAO plus
Because,
shoes.
sorry?
BAO with shoes. Or just
No, just BAO. So BAO in the sense that it forces a correlation between RS drag and H naught. Okay, so this is where BAO tells you have to be. And then Planck is somewhere here. Okay? So let's put the number here. So this would be 67 or so. And now let's put the RS drag numbers. So Planck tells you that this is something like 145 megaparsecs. But if you want, so I said we can take BAO and combine it with Shoes to get RS drag. Then RS drag has to be something like 137. Okay? So this is really the tension. The tension is an H naught RS star tension, and not a Hubble tension. And the reason it's important to look at it like this is that a lot of solutions that you would think would help get you Planck and Shoes to agree operate perpendicularly to what BAO forces you to do. Okay, so if you don't include BAO in your analysis, you would think, okay, maybe I can take Planck and I can play with omega matter. Okay, let's play with omega matter. It turns out that playing with omega matter, for example, changing omega matter moves the Planck result along this axis. But you can't do that because then you don't agree with BAO. Okay? So it's actually more complicated. If you don't treat the tension as this tension, then you're not going to get the right solution. Okay? Or a consistent solution. Yeah.
How far are we from getting some confirmation of the Shoes result, so measuring it by other means? Right, so we have BAO plus DDM that gives you like an independent determination of the early universe measurement. But the Shoes, it seems like it depends on many different runs of this ladder that I don't know how trustworthy they is.
Okay. So let's just summarize that we need a 7% change, okay? Around a 7% change if we want to reconcile RS drag or the Shoes measurement. That is the size of the effect. And of course, how robust this is, so that was how robust this is depends on how robust this measurement is. And as you just said, this is robust to CMB anisotropies, for example, because you can use this alternative route, which is still an early universe route. The question is, you're asking is how robust is the Shoes part? So what we said yesterday is that what Shoes does is it goes from distance to Cepheids to type 1a supernovae. So there are other groups which use, instead of Cepheids, use some other calibrator. Okay, so there are, I think, do I have still time? Because I want to talk about this tomorrow in a little bit more detail, but when I summarize. But there are other ways to calibrate this distance ladder. Instead of Cepheids, which are one type of standard candles, there are other types of standard candles. One is called tip of the red giant branch, and one is called Myras stars, which is a type of star for which there is also a feature that tells us what the intrinsic luminosity of that star is, similar to Cepheids, where it's the period of the variability of the luminosity that does that. And you can use these calibrators to get you to the type 1a supernovae, still using type 1a supernovae. And I can show you how these results behave, agree or not, or do not agree with Cepheids, but they're fairly consistent with Cepheids. There's a question about this one. And then there's, I mentioned this yesterday, there are measurements of time, lensing time delay of quasars. Those also get you values that are consistent with Shoes, more or less. And there are several other methods that have been proposed, and I think I'll leave that for tomorrow. Okay?